On March 4th, 2026, a fault line off Alaska moved. No headlines, no breaking alerts, no dramatic footage, just a magnitude 6.4 earthquake swarm on one of the most dangerous plate boundaries on Earth. The exact same fault that sent a wall of water across the Pacific in 1946 and killed over 150 people in Hawaii who never saw it coming. Tsunami evaluation systems flagged it immediately. Scientists went on record saying a stronger earthquake is now elevated risk. And somehow, nobody is talking about it. That silence isn't reassurance. That silence is the story. Stay with me until the end, because what I'm about to show you about this fault line should genuinely concern every person living on a Pacific coastline. Subscribe and follow along, because this sequence is not closed. The fault is still being watched, the aftershock window is still open, and the researchers monitoring the Western Aleutian Arc are not done running their models. When the next development lands, this channel breaks it down first. You'll want to be here. Now, let's get into it. Something happened on March 4th, 2026, and almost nobody noticed. A magnitude 6.4 earthquake tore through the seafloor near the Western Aleutian Islands, approximately 224 kilometers east-southeast of Attu Station, Alaska. The ground moved. The ocean registered it. Monitoring systems around the Pacific lit up. And then, the news cycle shrugged and moved on. Let's not do that. Because this particular earthquake, in this particular location, deserves a much closer look than it got. The quake struck along one of the most mechanically violent boundaries on the surface of this planet, the Aleutian subduction zone, where the Pacific plate is actively diving beneath the North American plate. This isn't a subtle geological relationship. This is one tectonic plate slowly consuming another, grinding downward into the mantle at roughly 7 to 8 centimeters per year. It doesn't sound like much, but multiply that motion across millions of years, and you start to understand why this region has a history that reads less like a geological record and more like a list of disasters. Now here's where it gets interesting, and I want you to pay attention to this part. The magnitude 6.4 was not a standalone event. It was the largest quake in a rapidly developing sequence, what seismologists call a swarm, that had been building in the same location over the preceding hours. The sequence went like this: a magnitude 5.4 foreshock, then the magnitude 6.4 main event, then a magnitude 4.9 aftershock, followed by a magnitude 4.5 aftershock. All of these earthquakes occurred within hours of each other, all of them at nearly identical coordinates. That tight clustering is not random noise. It indicates activity along a specific, single fault segment, one section of the plate boundary that is experiencing a concentrated episode of stress release. The USGS assigned the event what's called a green pager alert. That's their way of saying low expected casualties, low expected structural damage. And technically, that's accurate. The epicenter sits near Attu Island, one of the most remote places in the entire United States, where the permanent civilian population is exactly 0. So in terms of immediate human impact, this earthquake ranks pretty low on the urgency scale. No collapsed buildings, no footage from panicked streets, no dramatic rescue operations. But here's the detail that caught my attention, and it's the reason we're having this conversation today. 2 of the earthquakes in that sequence triggered tsunami evaluation flags from the National Tsunami Warning Center. The monitoring system registered conditions that warranted immediate assessment. Scientists began publicly circulating a statement that carries wording you don't hear very often from people trained to measure their language carefully. The statement said, and I'm paraphrasing slightly here, that the risk of an even stronger earthquake is now elevated. Scientists rarely say things like that out loud unless the pattern they're looking at genuinely concerns them. And the question that nobody in the mainstream press seems to be asking right now is a fairly important one. Is the earthquake sequence over, Or is this how something much bigger begins? The sequence that preceded the magnitude 6.4 didn't just appear out of nowhere. The cluster began roughly 2 days before the main event, with smaller earthquakes registering in the same region. Early tremors that, in hindsight, were almost certainly the fault warming up. Seismologists study these kinds of patterns obsessively, and for good reason. When multiple earthquakes occur rapidly along the same fault segment, scientists sometimes refer to it as an earthquake burst. The tight sequencing suggests that one section of the plate boundary is undergoing an accelerated period of strain release, almost like a pressure valve opening in stages. And the specific progression here is one of the most studied, and frankly, most nerve-wracking patterns in all of seismology. Think about what the sequence looked like. A magnitude 5.4, followed hours later by a magnitude 6.4, followed by smaller aftershocks. Under normal circumstances, if you're a seismologist watching that unfold in real time, you ask yourself a question that has no comfortable answer. Was the 6.4 the main shock, meaning the biggest event in the sequence, or was it a foreshock to something even larger still to come? This distinction matters enormously, and history gives us reason to take it seriously. In March of 2011, a magnitude 7.2 earthquake struck off the northeastern coast of Japan. Scientists noted it. Monitoring systems registered it. And then, 2 days later, the magnitude 9.0 Tohoku earthquake happened. The 7.2 had been a foreshock. Nobody knew that at the time. In 2016, a magnitude 6.2 earthquake struck the Kumamoto region of Japan. It was initially treated as the main event. Then, within 24 hours, a magnitude 7.0 hit the same region. Again, the first quake had been the opening act. These are not obscure historical footnotes. These are reminders that earthquake sequences don't always follow a neat, predictable order. Sometimes the largest event occurs first, and the rest are aftershocks. But sometimes the sequence is building, not winding down. The problem, and this is what makes seismology genuinely humbling as a science, is that in the early hours of a developing sequence, you often cannot tell which scenario you're in. The Aleutian region experiences earthquake swarms with some regularity. This is a tectonically active zone, and seismic activity here is, in some sense, expected. But what scientists noted about this particular cluster was the unusual tightness of the coordinate grouping. These earthquakes weren't scattered across a broad region. They were stacked almost on top of each other, geographically speaking, which suggests concentrated stress release along a very specific locked section of the plate boundary. And when stress releases in one place, it doesn't just disappear. It redistributes. It moves to adjacent sections of the fault. And somewhere along the chain, that redistributed stress has to go somewhere. The question of where it goes next is one that nobody can answer with certainty right now. But tsunami evaluation systems were already trying to figure out exactly how seriously to take this sequence. And the reason they care so much about this particular stretch of ocean floor will take us somewhere genuinely unsettling. Somewhere in a monitoring center, an algorithm registered the magnitude 6.4 and immediately began running calculations. Not about ground shaking, not about structural damage, about waves. The USGS earthquake detection system automatically flags events that carry tsunami generating potential, and both the magnitude 6.4 and the magnitude 5.4 earthquakes in this sequence carried what's called a tsunami equals 1 flag. That notation means the system detected conditions potentially capable of generating ocean waves and immediately triggered a formal evaluation by the National Tsunami Warning Center. To be absolutely clear, this does not mean a tsunami occurred, but it means the systems designed to catch tsunamis before they become disasters treated these earthquakes as worth watching in real time. The National Tsunami Warning Center runs its evaluation using a combination of tools. Seafloor pressure sensors scattered across the ocean floor can detect the subtle pressure changes that a passing tsunami wave creates. Tide gauges at coastal stations measure sea level with enough precision to identify anomalous wave activity. Seismic data feeds in continuously, helping analysts understand the geometry of the rupture, because the angle and orientation of a fault's movement matters enormously in determining whether a quake generates significant wave energy or not. A magnitude 6.4 earthquake on a subduction zone under the ocean is, depending on its mechanics, technically capable of generating small local tsunami waves. The Aleutian Trench is precisely that kind of environment, a deep ocean subduction boundary, where the seafloor geometry creates the conditions for upward water displacement when stress releases suddenly. The ocean doesn't know the difference between a seismic event that humans consider minor and one they consider catastrophic. All it knows is whether the seafloor moved, how much, and in which direction. Now, to generate a genuinely destructive Pacific-wide tsunami, the kind that travels across an entire ocean basin and kills people on distant coastlines, you typically need an earthquake of magnitude 7.5 or larger. The 6.4 doesn't cross that threshold on its own. But here's why the tsunami monitoring systems don't simply ignore smaller events in this specific region. Historical precedent, because the Aleutian Arc has already demonstrated multiple times that it is capable of generating exactly those catastrophic ocean-crossing waves. And when an earthquake happens here, even a moderate one, the systems built specifically to prevent another catastrophe are not in the habit of looking away. There is something worth sitting with here. The Aleutian Islands are not primarily dangerous because of ground shaking. The nearest population centers are hundreds of kilometers away. The danger isn't buildings falling. The danger is what the fault can send across thousands of kilometers of open ocean, arriving hours later on coastlines full of people who may have no idea anything happened. And that history, that specific documented deadly history, is what we need to talk about next. Despite triggering tsunami evaluation systems, despite a statement from seismologists using elevated risk language, despite occurring along one of the most capable fault systems on the planet, this earthquake sequence received almost no mainstream media coverage. Go ahead and search for it. I'll wait. The primary reason for the silence is geography, and it's almost paradoxical when you think about it. The epicenter lies near Aleutian Island, which holds a specific geographic distinction. It is the westernmost point of the United States. Aleutian sits so far west that it actually crosses the 180th meridian, technically placing it in the eastern hemisphere by longitude, even though it's American territory. It is genuinely one of the most remote places you can be while still standing on U.S. soil. There is no permanent civilian population on Aleutian. The island once housed a significant military installation and was the site of one of the only World War II land battles fought on American soil. A brutal, largely forgotten campaign in 1943. But today the island is essentially abandoned. No residents, no infrastructure worth mentioning, no one to call in a damage report, no one to post footage to social media, no one to appear on camera looking distressed in front of a ruined building. And media coverage, as any journalist will tell you, follows visible human impact. No people, no story. It's also worth noting the timing. At the moment this earthquake sequence was developing, the continental United States was dealing with hundreds of active weather alerts, severe storm systems, winter weather events, the kind of multi-state meteorological situation that dominates every available news segment. The earthquake, happening silently under a remote stretch of the North Pacific without hurting anyone immediately visible, simply did not compete. And yet, historically, some of the most destructive tsunamis ever recorded in the Pacific originated in this exact region. The same stretch of fault line that produced a magnitude 6.4 this week has produced earthquakes 2 full magnitude units larger, events that sent walls of water racing across the Pacific at the speed of a commercial jet. The silence around this earthquake isn't evidence that it doesn't matter. It might actually be evidence of the opposite. Because the earthquakes from this region that mattered most, the ones that killed people thousands of kilometers away, also began quietly. They began with the ground moving somewhere remote, where nobody was watching, where no cameras were rolling. The real story here isn't the magnitude. The real story is the fault line behind it. And that fault line has a history that should be part of every conversation about Pacific risk that isn't happening right now. To understand why a magnitude 6.4 earthquake in a place most people couldn't find on a map deserves serious attention, you have to understand the structure beneath it. The Aleutian Islands don't exist by accident. They are the surface expression of one of the most mechanically extreme geological processes operating on Earth right now: oceanic subduction. The Pacific Plate is moving. It has been moving for tens of millions of years, driven by the slow convection currents churning through the mantle below. In the northern Pacific, this motion carries the plate in a roughly northwestern direction, and when it reaches the boundary with the North American plate, it doesn't stop. It can't stop. The only option, given the physics involved, is to go down. So it does. The Pacific Plate dives beneath the North American plate at the Aleutian Trench, descending into the mantle at approximately 7 to 8 centimeters per year. 7 to 8 centimeters. The length of a credit card, roughly, per year. It sounds almost quaint until you consider that this motion is continuous, relentless, and operating across a boundary that stretches approximately 2,500 kilometers across the North Pacific. The Aleutian Arc curves in a long, sweeping arc from the Alaskan mainland in the east all the way to the Kamchatka Peninsula in the west, forming a chain of volcanic islands that separate the Pacific Ocean from the Bering Sea. Every single one of those islands exists because subduction generates magma, and magma finds a way to the surface. The mechanics of this boundary create the ingredients for the largest earthquakes on Earth. When two plates meet at a subduction zone, they don't always slide past each other smoothly. In many sections, the plates lock together. The overriding plate grips the subducting plate like two hands clasped together, preventing motion. The relative motion between the plates doesn't stop, but it can't be expressed as movement. Instead, it accumulates as elastic strain in the crust. Year after year, decade after decade, the strain builds. The rock bends. The stress accumulates. Until eventually, the grip fails. The locked section ruptures, and all of that accumulated strain releases in seconds as a megathrust earthquake. The Aleutian Trench has produced multiple earthquakes larger than magnitude 8.5. That places it among the most powerful seismic regions anywhere on Earth. And the fault that generated this week's magnitude 6.4 is the same fault that has, in its recorded history, produced events thousands of times more energetic than anything that happened this week. Think about that for a moment. The fault responsible for the minor tremor that didn't make the news has, on multiple occasions, produced earthquakes so large they sent waves across the entire Pacific Ocean. The Aleutian Arc's historical record reads like a catalog of the planet's mechanical extremes. Several major earthquakes have occurred along this boundary within the last century alone, and each one demonstrated not just the raw energy capacity of the system, but its ability to transfer that energy across oceanic distances in the form of tsunamis. In 1957, the Andreanof Islands section of the Aleutian Arc ruptured in a magnitude 8.6 earthquake. 8.6. To put that number in context, remember that the earthquake scale is logarithmic. Each full magnitude unit represents approximately 32 times more energy released. A magnitude 8.6 releases tens of thousands of times more energy than a magnitude 6.4. The 1957 earthquake generated tsunami waves that propagated across the Pacific Basin. Local run-up heights along sections of the Aleutian coastline exceeded 15 meters in some places. 15 meters is roughly the height of a 5-story building. The wave didn't ask for permission before arriving. 8 years later, in 1965, the Rat Island section of the same arc ruptured at magnitude 8.7. This is a section of the fault geographically close to where the current earthquake sequence occurred. That earthquake also produced tsunamis. The pattern is consistent. The mechanism is consistent. The Aleutian megathrust generates enormous earthquakes, and those earthquakes send waves into the Pacific. Now, here is the concept I want you to hold on to, because it becomes important very shortly. The fault that produced a 6.4 earthquake this week is capable of earthquakes 2 full magnitude units larger. 2 full units on the logarithmic scale. Each unit multiplies the energy by 32. So 2 units means 32 times 32, roughly 1,000 times more energy. 1,000 times more energy released from the same fault, in the same region, through the same mechanical process. The 6.4 was, in tectonic terms, a whisper from a system that is capable of a scream. And one of those screams, one specific event from the history of this fault, permanently changed how humanity monitors the ocean. It killed people who had no idea anything had happened, on an island thousands of kilometers away, on a morning that began as completely ordinary. That event is worth understanding in detail, because it's the reason tsunami monitoring systems exist in the first place, and it's the reason that when a 6.4 strikes this region, monitoring centers pay attention within seconds. April 1st, 1946. The date is almost grimly appropriate for an event that seemed, at first, impossible to believe. An earthquake struck the Aleutian Trench. Magnitude estimates have varied across different analyses, but assessments commonly place it around magnitude 8.6. The rupture occurred underwater, along the same basic fault system we've been discussing, the same subduction boundary, the same mechanical process of locked plates suddenly releasing. The ground moved, the seafloor deformed, and the ocean, as it always does when the seafloor moves suddenly beneath it, responded. The tsunami generated by the 1946 earthquake did not cause its primary destruction in Alaska, where it originated. Alaska was remote, sparsely populated, and largely unprepared, but also largely distant from the event. The tsunami's most catastrophic impact came hours later and thousands of kilometers away. The waves traveled across the open Pacific at speeds approaching 800 kilometers per hour, roughly the cruising speed of a commercial jet. They were virtually invisible in the open ocean. Wave heights of less than a meter spread across wavelengths of hundreds of kilometers. Ships at sea that day may have passed over the tsunami without realizing it. 5 hours after the earthquake, the tsunami arrived at Hawaii. What greeted the islands was not a subtle wave anomaly. Waves reached heights of 14 meters, 45 feet in some locations. In Hilo, on the Big Island, the destruction was catastrophic. The waves swept inland, obliterating buildings, carrying debris, and killing 159 people. They had received no warning. They had no warning system to receive. There was simply the ocean, and then suddenly the ocean was somewhere it had never been before, moving at a speed and with a force that left no time for response. The devastation at Hilo in 1946 is directly responsible for the existence of the Pacific Tsunami Warning System, which was established in 1949. That system, now vastly more sophisticated, with seafloor sensors and satellite links and real-time monitoring, is the exact system that evaluated the magnitude 6.4 and magnitude 5.4 earthquakes in the current sequence. The fact that it flagged those events immediately, that it ran its calculations within minutes, that it assessed tsunami potential before most people on the Pacific Rim were even aware an earthquake had occurred. All of that infrastructure exists because of what happened in Hilo on April 1st, 1946. Think about the chain of consequence there. 159 deaths in Hawaii, led to a monitoring system that today protects hundreds of millions of people around the Pacific. The tragedy became infrastructure. The disaster became the warning. And now, in 2026, that same infrastructure is watching the same fault line again. The question the monitoring system cannot yet answer, and this is the question that should be keeping certain researchers awake at night, is whether those 1946 and 1957 and 1965 events used up the stress along this section of the fault, or whether there are sections still locked, still accumulating strain, still waiting. There is a concept in earthquake science that sounds simple, but carries enormous implications. The seismic gap. A seismic gap is a section of a known active fault that has not experienced a major rupture in an unusually long time. The logic behind the concept is straightforward. If a fault is active, if the plates are still moving, if the forces driving seismicity are still operating, then a section of that fault that has been quiet for decades may simply be a section that hasn't released its accumulated stress yet. Not because the stress isn't there, because it hasn't found its moment. Several sections of the Western Aleutian Arc have not experienced major megathrust ruptures in a significant period of time. Seismologists who study this region have noted the pattern. Certain segments that produced large events in the mid-20th century have been followed by smaller activity, and some adjacent segments have remained notably quiet. The behavior of a fault system over time doesn't follow a simple schedule. Earthquakes are not trains running on a timetable, but the concept of seismic gaps remains an active area of research precisely because accumulated strain has to go somewhere eventually. It's important to be honest about the limits of this framework. Seismic gap theory is genuinely controversial within the seismological community. Not every quiet fault segment is storing energy for a future major rupture. Some of that stress may be released gradually through smaller earthquakes. Some may be accommodated through slow slip events, episodes of gradual fault movement that don't produce significant shaking at all, but quietly release accumulated strain over days or weeks. The Earth's crust is not a simple machine, and earthquake forecasting, even in the probabilistic sense, remains one of science's most humbling challenges. But here's what we can say with confidence. The recent magnitude 6.4 cluster occurred within a segment of the Western Aleutian Arc. It activated a specific section of a fault that is part of one of the most capable megathrust systems on Earth. Researchers will be analyzing the location, the depth, the focal mechanism of these earthquakes, essentially the geometry of how the fault moved, to understand what part of the plate boundary was involved, and what that might indicate about stress distribution in the surrounding region. And there's something else happening in this region right now. Something beyond just the earthquake sequence itself. Because when you zoom out from a single fault line and look at the broader pattern of activity around the North Pacific right now, the picture becomes interesting. The kind of interesting that makes a certain type of scientist reach for more coffee and open more monitoring windows. And I think you're going to want to hear about it. The Aleutian Arc is not only a seismic system, it is simultaneously a volcanic arc, and the volcanoes along this chain have not been idle recently. The same subduction process that drives the megathrust earthquakes also drives volcanism. As the Pacific Plate descends into the mantle, it carries water and other volatile compounds into the hot rock below, lowering the melting point and generating magma that rises through the overlying crust. The volcanoes of the Aleutians are, in a very direct sense, the surface expression of the same tectonic engine driving the earthquakes. Several Aleutian volcanoes have shown elevated activity in recent periods. Shishaldin volcano, one of the most active peaks in the chain, has experienced multiple eruptive phases in recent years. Great Sitkin, Pavlov, and Cleveland volcanoes have all registered periods of elevated unrest, characterized by increased seismicity, ground deformation, and emissions. The Alaska Volcano Observatory monitors these systems continuously, issuing aviation color codes that alert pilots to ash cloud hazards and providing ground-level assessments of eruptive potential. Now, the relationship between volcanic activity and seismic activity along the same arc is genuinely complex, and scientists are careful not to draw simple cause and effect relationships between individual events. An earthquake doesn't automatically trigger a nearby volcano, and a volcanic eruption doesn't automatically indicate that a major earthquake is imminent. These systems operate on different timescales and respond to different pressure dynamics. But they share a common driver, the subduction of the Pacific Plate. When that process accelerates stress release in one form, it doesn't necessarily relieve stress in adjacent systems. It may, in some circumstances, redistribute it. There is also the question of what elevated seismic activity around a volcanic system can indicate. In volcanology, swarms of small earthquakes near a volcanic center are sometimes interpreted as evidence of magma movement, fluid or melt forcing its way through fractured rock, generating tremor as it goes. A seismic swarm near an active volcanic arc can mean purely tectonic stress release. It can also mean something is moving below the surface that isn't just rock. Distinguishing between those two scenarios in real time is one of the core challenges of monitoring these systems, and it's one reason why researchers watch both the earthquake data and the volcanic data together, not in isolation. The recent earthquake sequence occurred in a region bookended by volcanic systems that are themselves in varying states of elevated activity. That doesn't prove anything, but it adds another layer to a picture that, even without it, was already worth examining carefully. The Aleutian event didn't happen in a vacuum. Zoom out on any real-time earthquake monitoring map right now, and the Pacific Rim is doing what the Pacific Rim always does, which is to say, it's active. The Ring of Fire, the roughly 40,000-kilometer horseshoe of subduction zones and transform faults encircling the Pacific Basin, produces approximately 90% of the world's earthquakes and accounts for the vast majority of the planet's most powerful seismic events. In the weeks surrounding the Aleutian sequence, notable seismic activity has occurred across multiple sections of the Pacific boundary. Japan's seismic networks have continued to register activity along the Japan Trench, the same boundary responsible for the 2011 Tohoku disaster. The Cascadia subduction zone, running along the Pacific coast of North America from Northern California to British Columbia, remains one of the most discussed potential sources of a future megathrust event among researchers. The Tonga Trench, the South American subduction zone along Chile and Peru, the Philippine sea plate boundaries. These systems are all active, all accumulating stress, all being monitored. This is not unusual. This is Tuesday on planet Earth. The point isn't that all of these systems are simultaneously approaching rupture. The point is that the Aleutian event belongs to a global context, not just a local one. Seismologists increasingly think about stress transfer on scales that go beyond individual fault segments. The idea that a large rupture in one section of a plate boundary can alter stress conditions in adjacent sections, sometimes hundreds of kilometers away. Think of the Pacific Plate as a rigid shell resting on the mantle below it. When one edge of that shell is forced downward in a sudden rupture, the stress redistribution doesn't stay local. It propagates. The magnitude and direction of that redistribution depends on the geometry and scale of the rupture, but the principle is well established in earthquake science. A large event in the western Aleutians could, in theory, alter stress conditions along adjacent sections of the same fault system, and potentially along sections much farther away. None of this means an earthquake somewhere else is now inevitable because of the magnitude 6.4. Magnitude 6.4 earthquakes don't have enough energy to meaningfully stress distant fault segments. But if the sequence in the western Aleutians represents the early phase of a larger rupture, if the 6.4 turns out to be a foreshock, then the stress redistribution implications become significantly more serious. And there is one more layer to add to this picture before we talk about what scientists are specifically watching right now. Here's where I want to be transparent with you. Because this is the kind of territory where the line between fringe theory and legitimate scientific inquiry gets genuinely blurry. And I think that ambiguity is worth sitting with, honestly, rather than just dismissing it. There is a long-standing and largely controversial hypothesis in geophysics that solar activity, specifically periods of elevated solar wind, geomagnetic storms, and high-energy particle flux, may have some influence on earthquake triggering. The proposed mechanisms vary. Some researchers have suggested that geomagnetic fluctuations could influence the ionosphere and upper atmosphere in ways that, through poorly understood coupling mechanisms, affect stress in the lithosphere. Others have pointed to potential correlations between cosmic ray flux and seismicity, arguing that ionization effects might influence rock fracture mechanics at depth. A smaller subset of researchers has looked at gravitational tidal forces, not just from the moon, but from planetary alignments, as potential earthquake modulating factors. To be completely honest with you, the mainstream seismological community is skeptical of these hypotheses. Very skeptical. The proposed mechanisms are either physically implausible, given what we know about the energy scales involved, or the correlational studies that have been published have failed to survive rigorous statistical scrutiny. Earthquake catalogs are long, and seismicity is frequent, which means if you look hard enough for correlations with external variables, you will find apparent patterns that are almost certainly coincidental. But here's the thing. The March 4th, 2026 earthquake sequence occurred during a period of elevated solar activity. The current solar cycle, Solar Cycle 25, has been significantly more active than the previous cycle, with multiple X-class solar flares and several strong geomagnetic storms recorded in recent months. Whether this has any physical relationship to the earthquake sequence is, at the current state of scientific knowledge, genuinely unknown. Not disproven. Unknown. And for a channel that covers space weather and pushes back against the assumption that mainstream science always has the complete picture, I think intellectual honesty requires acknowledging that distinction. I'm not telling you solar activity caused the Aleutian earthquake. I am telling you that the intersection of elevated solar activity and elevated seismic activity in a location that humans have been studying for less than 100 years should at minimum generate questions. The Earth is not a closed system. It exists within a space environment that actively delivers energy to its surface in forms ranging from ultraviolet radiation to charged particle streams to electromagnetic flux. How that energy interacts with the geological systems at the planet's surface is not a question that has been fully answered. I'm going to tell you something that is almost certainly a coincidence. And I'm going to tell you it anyway, because context is everything. And because sometimes the most interesting questions come from noticing things that mainstream coverage doesn't bother to juxtapose. In the same general time frame as the Aleutian earthquake sequence, near-Earth asteroid monitoring systems were tracking multiple objects, making relatively close approaches to Earth. This happens constantly. The Planetary Defense Detection Network tracks hundreds of objects, and close approaches in astronomical terms can still mean millions of kilometers of distance. None of the objects tracked during this period posed any actual impact threat. This is not a story about an asteroid striking the Earth, but the Chicxulub impactor, the asteroid whose impact 66 million years ago triggered mass extinction, didn't just kill things. Through direct impact, the shockwave, the ejecta, the global atmospheric effects, and critically the seismic energy transmitted through the planet's crust affected geological systems globally. Large bolide impacts are, among other things, among the most powerful seismic events the planet can experience. The relationship between extraterrestrial inputs and geological response is not purely theoretical. It's documented in the geological record. Again, no asteroid hit Earth this week. The objects being tracked pose no threat. I want to be completely clear about that. But here is the genuinely interesting scientific question that this juxtaposition raises. What is the full catalog of external forcing mechanisms that can modulate stress conditions in the Earth's crust. We know tidal forces matter. The moon's gravitational influence measurably affects earthquake timing in some fault systems. We know that heavy rainfall can trigger shallow earthquakes by increasing pore water pressure. We know that large surface dewatering, emptying reservoirs, for example, can induce seismicity. The list of external triggers for seismicity is longer than most people realize. The asteroid observation isn't the story. The question it raises is the story. How thoroughly do we understand the boundary between the Earth system and the space environment it exists within? And is our current earthquake monitoring framework asking all the questions it should be asking? Because the stakes, especially along a fault system like the Aleutian Arc, could not be higher. Right now, as data from the Aleutian sequence continues to accumulate, seismologists are working through a specific analytical process that the public rarely gets to see in real time. The fundamental question driving that process is whether the magnitude 6.4 was the main shock, the primary stress release event, or whether it was a foreshock in a sequence that hasn't reached its largest event yet. This question is not answerable with certainty in the immediate aftermath of a swarm. What scientists can do is assess probabilities based on empirical models of how sequences typically evolve. The standard tool used for this kind of assessment is a statistical model called the Omori-Utsu law, which describes how aftershock rates decay over time following a main shock. If the magnitude 6.4 was the main shock, aftershock rates should be declining on a predictable curve. If instead the sequence is still building, if stress is continuing to transfer rather than dissipate, the rate curve may deviate from the expected pattern. The depth of the earthquakes in the sequence also matters. Deeper earthquakes along a subduction zone tend to behave differently from shallow crustal events. The 1946 and 1957 megathrust events involved rupture in the shallow subduction interface, the actual contact zone between the Pacific Plate and the North American Plate. If the current sequence is occurring on that same shallow interface, the implications are different than if it's occurring in the downgoing slab itself at depth. Focal mechanisms, essentially the geometry of how the fault moved during each earthquake, are another key piece of information seismologists extract from the waveform data. A thrust fault mechanism along the subduction interface is the type most associated with large tsunami-genic earthquakes. A different fault geometry, such as a normal fault or strike-slip motion, while still capable of generating waves, carries different implications for maximum magnitude potential and wave generation efficiency. These analyses take hours to days to fully resolve, which means the picture scientists are looking at right now is still incomplete. And incomplete pictures are exactly where surprises hide. One of the most active areas of current seismological research involves understanding how stress changes in one section of a fault system affect other sections nearby. This field, sometimes called Coulomb stress transfer analysis, has produced some genuinely important insights about earthquake clustering and triggered seismicity. The basic principle is that when one section of a fault ruptures, it doesn't just release the stress stored in that specific section. It alters the stress state of the surrounding crust, sometimes increasing stress on adjacent fault segments, sometimes decreasing it. In the context of the Aleutian Arc, this means that the current earthquake sequence, regardless of whether the 6.4 represents the end of the story or the beginning, has changed the stress environment along nearby sections of the same fault system. Calculating exactly how it's changed requires knowing the geometry, depth, and magnitude of the rupture in detail, and running those parameters through stress models that account for the elastic properties of the surrounding rock. This kind of analysis is underway for virtually every significant earthquake sequence in a high-risk region. The segments of the Aleutian Arc most relevant to this analysis are those immediately adjacent to the current sequence epicenter. In the eastern direction, the arc runs toward the Aleutian Islands segment, the section that produced the magnitude 8.6 earthquake in 1957. In the western direction, the arc approaches the near island segment and eventually the area near Attu itself. These segments have their own history, their own periods of activity and quiet, and their own accumulated stress profiles that researchers have been estimating from GPS measurements of ground deformation and from historical earthquake records. The near-field effects of stress redistribution are typically the most significant. A moderate earthquake, like the 6.4, can meaningfully change stress conditions on adjacent segments of the same fault within a distance of roughly 2 to 3 times the fault rupture length. For a magnitude 6.4, the rupture length is on the order of 15 to 20 kilometers, which means the most significant stress perturbations affect sections of the fault within perhaps 50 to 60 kilometers of the rupture zone. That's not nothing. In a fault system where individual segments can be hundreds of kilometers long, it's a local effect. But local effects have, in documented cases, been enough to bring a nearly ready segment to failure. The question of what it actually takes to generate a destructive Pacific-wide tsunami is worth examining in detail, because the answer is more nuanced than a single magnitude threshold suggests. Magnitude 7.5 is commonly cited as the lower bound for tsunami-genic earthquakes capable of causing distant coastal damage, and that's a useful heuristic. But the actual wave generation depends on a combination of factors that vary case by case. The depth of the earthquake is critical. A shallow subduction zone earthquake, occurring at depths between 10 and 30 kilometers on the interface, is far more efficient at displacing the seafloor, and therefore the overlying water column, than a deeper event in the subducting slab. A shallow thrust fault earthquake at magnitude 7.5 on the Aleutian interface would be a significantly more serious tsunami threat than a deeper event of the same magnitude. The area of the rupture zone matters. Larger rupture areas displace more seafloor, generating higher and more energetic wave fronts. Earthquakes that rupture longer sections of the fault generate proportionally larger tsunamis, and the relationship between rupture area and wave height is not linear. It scales in ways that make very large earthquakes disproportionately dangerous, as tsunami sources compared to their magnitude alone might suggest. The orientation of the fault relative to the ocean basin affects where the tsunami energy is preferentially directed. An earthquake on the Aleutian Arc preferentially sends energy south, directly toward Hawaii and toward the western coast of North America. The geometry of the Aleutian Trench acts almost like a wave gun pointed at the populated coastlines of the northern Pacific Rim. This is not a coincidence of recent interest. It's the documented pattern from every major Aleutian tsunami-genic earthquake of the 20th century. Hawaii is approximately 5 hours of tsunami travel time from the Aleutian source zone. The Pacific coast of North America is approximately 3 to 5 hours depending on location. Japan is roughly 8 hours. These travel times are long enough for effective warning if monitoring systems detect the earthquake quickly and characterize the tsunami potential accurately. But they are also short enough that any failure in the warning chain, any delay in detection, any miscommunication, any underestimation of tsunami potential could translate directly into preventable deaths. There is a category of seismic behavior that monitoring systems are only beginning to fully characterize, and its existence is one of the more sobering aspects of modern earthquake science. Slow slip events, episodes where fault movement occurs gradually over days, weeks, or months rather than suddenly in seconds, can transfer significant stress along plate boundaries without producing the kind of high-frequency seismic signals that traditional networks are designed to detect. In subduction zones including Cascadia, Japan, and New Zealand, researchers have documented these events using GPS networks sensitive enough to detect millimeter-scale ground surface movements. The Aleutian Arc's remoteness creates a significant monitoring gap in this regard. GPS monitoring infrastructure is sparse in the western Aleutians. Seafloor monitoring equipment, while present, provides less spatial coverage than the dense onshore networks available in more accessible regions. This means that slow slip events, which in some models are hypothesized to precede major ruptures by days to weeks, could be occurring along the western Aleutian interface without being detected in real time. The geodetic monitoring gap, the gap between what GPS networks and seafloor instruments can actually observe versus what is physically happening along the entire fault boundary, is one of the recognized limitations of current hazard assessment for the Aleutian Arc specifically. Researchers have advocated for expanded monitoring infrastructure in this region for years. The cost and logistical challenges of deploying and maintaining instruments in one of the world's most remote and climatically hostile environments have slowed that expansion. What this means practically is that some of the data scientists would most want to have when assessing the current sequence's implications is simply not available. They are reading a story with pages missing. The monitoring systems that do exist, the seismic networks, the dart buoys in the ocean, the tide gauge networks are powerful and sophisticated, but they are working with incomplete information about what is happening at depth along a fault system that is capable of generating one of the most destructive natural events on Earth. The Aleutian megathrust has been accumulating stress for a long time, not just since the last major rupture, but continuously as the Pacific Plate grinds northwest at its steady 7 to 8 centimeters per year. The question of how much stress has built up in any given segment of the fault since its last significant rupture is one that researchers attempt to quantify using what's called a seismic moment budget, essentially an accounting of how much strain energy has been added to the system versus how much has been released through earthquakes. The 1946, 1957, and 1965 earthquakes released enormous amounts of strain energy along their respective sections of the arc, but those events were localized to specific segments. The Aleutian Arc is 2,500 kilometers long. Not every section ruptured in those mid-20th century events, and the sections that didn't rupture have had decades to accumulate additional strain while the plates kept moving. To put approximate numbers on this, at 7 centimeters per year, the accumulated plate motion since 1965, 61 years, amounts to roughly 4.3 meters of relative plate displacement. In a segment that is locked, that 4.3 meters of motion hasn't been expressed as smooth sliding. It's been stored as elastic strain in the rock. And the mechanical relationship between accumulated displacement and eventual earthquake magnitude is well established. A locked fault segment of sufficient area with several meters of accumulated displacement has the potential to produce a major megathrust earthquake when it finally releases. This is the arithmetic of catastrophe. It doesn't predict when. It doesn't specify which segment. It doesn't tell us whether release will come in a single large rupture or gradually through smaller events over decades. But it establishes the physical reality. The energy is there. The fault is capable of releasing it. And the current earthquake sequence occurred in a region where that calculation is not theoretical. It's a description of current geological conditions. If the Aleutian Arc were to produce a major megathrust earthquake tomorrow, magnitude 8 or greater, shallow interface rupture, significant seafloor displacement, the tsunami threat would unfold over the following hours in a very specific geographic pattern that's worth understanding clearly. Hawaii would receive the first major wave energy approximately 5 hours after the earthquake. The city of Hilo on the Big Island of Hawaii has been struck by major Aleutian tsunamis before, in 1946 and again in 1960, when a Chilean earthquake sent waves across the Pacific. Hilo sits on a bay that acts as a natural funnel for incoming wave energy, amplifying tsunami heights above what surrounding coastlines experience. Despite modern warning systems and evacuation infrastructure, the 5-hour window for a far-field tsunami warning is manageable only if the warning is issued quickly and the public responds without hesitation. Studies of evacuation compliance in tsunami warning scenarios suggest that a significant fraction of people in affected zones don't leave even when warned. The Pacific coast of North America, Oregon, Washington, Northern California, British Columbia would receive tsunami energy within approximately 3 to 5 hours. These coastlines are home to coastal communities that have their own complicated relationship with tsunami risk. The dominant narrative in Pacific Northwest hazard planning focuses on the Cascadia subduction zone, which could produce a local tsunami with arrival times of 15 to 30 minutes, far too fast for any warning system to be effective for nearby communities. A far-field Aleutian tsunami arriving hours later would actually allow warning time, but that warning window requires that people know what to do, that they take it seriously, and that they actually move to higher ground. Japan, Kamchatka, and other Western Pacific coastlines would face tsunami energy approximately 8 to 10 hours after an Aleutian rupture. The Japan Meteorological Agency has among the most sophisticated tsunami warning systems in the world, rebuilt and enhanced significantly after the 2011 disaster. But 2011 also demonstrated that even excellent warning systems cannot fully compensate for the scale of energy that a major subduction zone earthquake can release. The pattern here is consistent and documented. An Aleutian megathrust doesn't just threaten Alaska, it threatens the entire Pacific Basin on a timeline measured in hours, affecting populations that may have no awareness of what just happened on a remote stretch of seafloor thousands of kilometers away. There is a phrase used in disaster risk research, the quiet interval problem. It describes the tendency of populations and institutions to discount the probability of rare but catastrophic events as the time since the last such event increases. The less recently something terrible happened, the harder it becomes to sustain the social and institutional attention required to prepare for it happening again. The last Pacific-wide catastrophic tsunami from the Aleutian Arc occurred in 1946. That's 80 years ago. 80 years is more than a human lifetime. The people who were alive in Hilo when the 1946 waves arrived are overwhelmingly gone now. The institutional memory of that event persists in warning systems and evacuation plans, but the lived, visceral understanding of what those waves looked like and what they did has faded from collective experience. The 2011 Tohoku tsunami reset global awareness of tsunami risk, at least temporarily. It produced footage so graphic and so widely distributed that it briefly made abstract risk feel real and immediate to hundreds of millions of people around the world. But that awareness fades too. Infrastructure ages. Budget priorities shift. New populations move into coastal zones without clear understanding of what living adjacent to a tsunami-prone ocean actually means in practice. And here's the deeper problem. The Aleutian Arc occupies a particular psychological position in the geography of risk perception. It is remote enough that it rarely generates attention, active enough that it is constantly producing moderate seismicity, and capable enough that it has multiple documented cases of generating catastrophic Pacific-wide tsunamis. It is, in a sense, the most dangerous kind of hazard, one that the people most at risk have mostly stopped thinking about. The magnitude 6.4 earthquake that didn't make the news this week is a direct expression of that perception gap. An earthquake sequence on one of the planet's most capable fault systems, with tsunami evaluation flags and elevated risk statements from scientists, went largely unnoticed. Not because nothing happened, because the something that happened was happening in the wrong place to command attention. Here is where we stand right now, and I want to be honest with you about what we know and what we don't. The magnitude 6.4 earthquake sequence in the Western Aleutians may be over. The main event may have occurred. The aftershock sequence may decay on a normal curve over the coming days, and the fault segment involved may return to the quiet accumulation of stress that characterizes the intervals between significant events. That is the most likely outcome, statistically speaking, but it may not be over. The sequence may represent the early stage of a larger cascade of stress release along this section of the plate boundary. The 6.4 may, in the fullness of retrospective analysis, be classified as a foreshock to a larger event that has not yet occurred. There is no scientific method currently available to distinguish between these two scenarios in real time, which is one of the most profound limitations of earthquake science as a practical tool for hazard management. Scientists are watching. The monitoring systems are running. The dart buoys positioned in the Pacific are ready to detect any anomalous wave signature within minutes of generation. The National Tsunami Warning Center has the capability to issue alerts for Pacific coastlines within 3 to 5 minutes of detecting a tsunami-genic earthquake. The infrastructure built on the lessons of 159 deaths in 1946 is functioning and alert. But infrastructure is only part of the story. The other part is the 300 million people living on Pacific coastlines, who mostly don't know that a magnitude 6.4 earthquake swarm just occurred on the fault that created the modern tsunami warning system. They don't know because nobody told them. They don't know because the news cycle moved on to other things. They don't know because remote seismicity rarely competes with the noise of a world that has a very short attention span and a very deep collective tendency to assume that catastrophic things happen to other people at other times. The Aleutian arc does not operate on a human news cycle. It does not check whether we're paying attention before deciding to release accumulated stress. It has been moving, grinding, accumulating, and occasionally rupturing for millions of years. It will continue to do so regardless of whether any given magnitude 6.4 earthquake makes a trending list or gets scrolled past on a Tuesday afternoon. The question is not whether this fault system will eventually produce another catastrophic event. It will. Every megathrust system in the world's geologically active margins will, on timescales that may be decades or centuries, but that are, in the context of the system's history, essentially imminent. The question is whether, when the sequence that matters finally begins, humanity will be paying enough attention to the signals that precede it, or whether once again the first warning anyone gets will be the water. Sleep well, and maybe keep one eye on the monitoring feeds.